All right, here we go. Let's get it going here. First of all, congrats on finishing the first half of calculus, all about derivatives. We are now starting the second half, which is called integration or integrals, which is the opposite of derivatives. So really, we're going to spend the rest of the year doing the opposite of what we just did. So let's take a look at the example, explain what's going on here to kind of give us a foundation. Imagine you got a car that's going 60 miles an hour. So it's just a nice velocity. It's a flat right here. Draw a straight line. And this is my time down here, and this is in hours. So my y-axis is the miles per hour. So I'm looking at this rate of change. I'm looking at this velocity function, and it's a nice, easy one. So why do we need antiderivatives? We're going to why we need antiderivatives. Essentially, this problem's pretty nice because let's say I want to know how far did you go between 1 and let's go 4. Between 1 and 4 hours, how far did you travel? Well, that's kind of easy. Like you just say in 3 hours, you went what? Because that's between 1 and 4. 3 hours at 60 miles an hour, you went 180 miles. So we don't need calculus for this example, but coming up we will. So if I look at this picture, yeah, I know the answer is 180. So if I look at the area under the curve, that's what this whole idea of these antiderivatives are. Ooh, those are some straight lines. Look at that. That's impressive. It's the area under the curve. So if you find the area under the curve of this rate of change of this miles per hour, and it's going to take me a while to shade that bad boy in. I need a thicker marker here. But if I find the area of this, check out this. What is the width of this rectangle that I just drew? Well, it's 3, isn't it? And what is the height of it? If I go up, it is 60. 3 times 60, the area of that is 180. That is awesome. Super cool right there. So really, if we can use the area under the curve to find the total accumulation of whatever this function is. So you're like, wow, I didn't need to be able to do that. Yeah, not for that example, but for these examples coming up, check this out. Okay, so look at this. So let's say I want to find the area under the curve, and I'm going to do it like an orange here. So I've got a left endpoint rectangle for the interval 1 to 3 with n sub intervals, and I'll explain that here of this function. So here's my function right here, and I want to know essentially from 1 to 3, what is the area under the curve? Well, check it out. It's not a nice, easy rectangle, is it? I can't just do length times width to find this area. So that's what I'm looking for. We're going to approximate this area. So the whole idea of this section is making approximations of the area under the curve. So when you think of derivatives, you think of, oh yeah, rate of change, slope of the tangent line, instantaneous rate of change. Now, when you think of the opposite, we're going to say area under the curve. Awesome. So let's check this out. What does it mean? N subintervals means I want 2 rectangles to approximate this. So this is a left endpoint rectangle from 1 to 3. So at 1, you're going to draw in. It's going to hit its left endpoint, and I'm going to 1 to 3, so I know there are 2 rectangles. So this will be the first one. And then when I plug 2 in there, I'm going to come up here, and it hits right there and that. So these 2 rectangles are approximating that gold area, that orange area right there. Is it a good approximation? Not really, no. Can we calculate it pretty easy? Sure, the width of this is just 1. From 1 to 2 is 1. The height of that, if you can put in the function or you can look at it, it's 2. So it's a 1 by 2, so the area of that is 2. This width is also 1, and then what happens if you put 2 in? You're going to get 5. So what is this? The approximation is 7. Is that a good approximation? Not really. It's actually not that good. You can see all this orange here that I didn't account for. So it's too low. Like this is a low estimate. It's not good enough. So what can we do? Well, we can do more rectangles. What if we change this to 4 rectangles? So I'm going from 1 to 3, but this time I'm going to break it into 4 rectangles here. So check it out. I'm kind of making narrower rectangles now. And this is going to go up and hit here. This is going to go up and hit here. And this bad boy is going to go up and hit there. So now, check that out. Is that a better approximation? Yeah, we're getting there. Is it still good? Not really. What if we did 6 rectangles? So I'm going 1 to 3, so I'm going to change my n here. And I know I'm going to have to make this go 1, 2. There's going to be 3 in each of these to get my 6 rectangles. And again, I'm going left endpoint, so I'm going to go there until it hits the function. And it's going to come up and hit here. It's going to come up and hit here. Okay, I hope yours are a little straighter than mine here. Ooh, that one, nailed that one. And that bad boy right there. and then he's going to come over, boom. So check this out. So 6 rectangles, not too shabby, huh? There's a little bit less area under the curve, so I'm getting better. What would be even better? Well, check this out. So check out this picture. I've got that x squared plus 1 with the 4 rectangles with the left endpoint. And check it out as I add a rectangle. 5, 6, 7, 8, 9, 10. So I didn't want to draw all this out. That'd be crazy. But check this out. What's happening? What am I doing here? 15, 16, 17, 18, 19, 20. Oh my goodness. I'm up to 30, 40, 50. Yeah, I'm all the way out to 100. They're so small you can't even see them. What does that represent? Look at that. That's the area under the curve. And I'm only at 100 rectangles. Imagine if I was at 1,000,000 or 1,000,000,000, or maybe even the limit as x approaches to infinity. I don't know. So I want an infinite amount of rectangles. That'll get me the complete area under the curve because those rectangles will be so small. Each little slice is going to give me the area under the curve. I'm not going to sit here and try to draw n is 100 or 1,000 rectangles, so I'm going to be okay with my estimate. Let's just do this one with 4. So what I want you to see is some important things here going on. So how wide is each of these? Well, you can look at this picture and say, oh yeah, these are each a half, aren't they? They got to be a half wide. Well, is there a way to get that? Sure. How do I get that? If this is my interval, we're going to say from A to B. What we're going to do to find the width is we're going to say B minus A, so B minus A all over the n sub-intervals. So this is going to give you the width of each sub-interval. So this is the width right here, b minus a over n. So in this case, if we didn't know this, I would just say, sure, my interval is from b to a, 3 minus 1 all over 4, which is 2 over 4, which is the 1/2. Same thing if I want to do it with 6, it's still 3 over 1. That's where I'm going. So this can change whatever your interval is. This time I'm going to divide it by 6 though, so I go 2 6, or each one of these is a third. And you can see they look like they're a third, like that. Awesome. So if I'm going to find this area, yeah, that was a nice easy one. What is this going to do? So I want to actually take some time to expand this out. So we're going to write this bad boy out. So let's write this out. So it's going to be a bit tedious, but we're going to write this out. So we're just going to do rectangle is base times height, or length times width. So the base is 1/2. And what am I timesing it by? Well, I can see it's 2 from the picture, but that is the f of 1. If I put 1 in there, yeah, I know 2 comes out. But I'm going to add this rectangle to it right here. And what do? It's still 1/2. That's its base. Except what is this point right here? It is the f of, what? 1.5? So it's 1/2 times that. Plus, what am I going to do? This rectangle right here. And what is the height of this? Well, it's 2 in this case, so it's going to be 1/2 times the f of 2. Plus the last rectangle, where does that hit? That's going to hit 2.5. So it's 1/2 the f of 2.5. Holy cow. So I can go ahead and do that. If I want now, just so I see it, they all have a half in them, don't they? So if I take that 1/2 out, let's go ahead and take that out. What's left? Well, it's going to be the height of the first rectangle, the f of 1, the height of the second rectangle, 1.5, the height of that is the f of 2, and then the f of 2.5. So I know it's a bit tedious. This whole section is a bit tedious. It's the longhand explanation, kind of like Mr. Bean explained the longhand definition of derivative. We're doing the same thing of the opposite of derivatives using these rectangles. So there it is right there. I know the f of 1, I can look at it and see, yeah, the f of 1 is 2, the f of 2 is 5, but I don't know the f of 1.5. So I would have to plug it into my function here, 1.5 squared plus 1, or I'm going to do it in the calculator. So let's just plug this bad boy in here. I've got x squared plus 1, and I'm going to change my table to, oh, I'm already there, great. So the independent should be on ask. You want to ask it questions, and if I go to my table, let's delete out anything I had in there. So I want to know the height of 1 was what? We knew that was 2. The height of 1.5, 3.25. The height at 2 and 2.5. So there are my 4 rectangles. There's the height of them. You can see it's, you can just add all these up now. So if I add these up, what do I get? Well, 2, 5, 7, and what is that? 10.5. So it looks like I get 17.5. So if I add up all those, I get 17.5. So let's come back to this. It'll be 1/2 times all those added up was 17.5. So what is 1/2 times 17.5? What is that? 8.75. 8.75. So the approximation of these 4 rectangles, the area there is 8.75. So you can see the rough, I started with 7, now I'm at 8.75. This will be even closer, n equals 8 will be even closer, n equals 10. But I want you to really write these out and see this here. I know it's a bit much, but it's really going to set us up for the next section explaining why all this stuff works. Awesome. So that was left-handed rectangles. What about right endpoint rectangles? So I can do the same thing, but remember I did the left endpoint. What if I'm going from 1 to 3, but now I want to do the right side? So what's the difference here? Well, if I do the right side in this case, and it changes depending on your function, well, what do you notice about these? Oh man, these are now all over estimates. Now I'm above, I have too much area. So check it out. Can we still do this with 1 to 3? Sure. I'm just going to do the same thing, but I'm starting on the right side. Starting on the right side, so I'm going to draw them all in there. Like this. And then notice these are above the curve in this case. And if they're above the curve like this, what we call this is circumscribed. I don't know if you remember back to geometry. Sometimes you had things that, like a circle would circumscribe a triangle or something. They're above the function, so we say this is circumscribed. Back here, these were inscribed. Now it's not because they're left endpoint or right endpoint. It's just because it's underneath. It's inscribed by the function. So you may see that every now and then. If it's underneath, it's inscribed. If it's above, it's circumscribed. So now these are highball estimates. These are too big. Let's finish this out. Just kind of have a little closure here. So if I do my right hand, and remember I said each subinterval was a third on this one, that whole b minus a thing. So I'm going to draw all my heights in. I think it's easier that way for this right here. And they're all the same intervals. And now I'm going to finish them off like this. There are all my rectangles. Awesome. So again, I can do the same thing here. Let's write out, but what's the difference? Let's do n equals 4 again, because that's what we were working on before. What's the difference here? Well, these rectangles are bigger. Let's write this out. So I know each one of these is a half. Remember, the width is a half. And I'm going to go ahead and say, what was the first right hand? Well, check it out. I'm starting with the f of 1.5 now. And now I'm going to plus the f of 2, plus the f of 2.5, plus the f of 3. So check it out. And I went ahead and wrote it with the interval out here. So that's all my my widths, or base times heights. So check it out. I went to the right-hand intervals. I'm doing this. So if I go back to my table, well, look at all the same numbers, aren't they? But I don't need 1 anymore, do I? I'm going to end on when the f of 3. So I changed that one number to 10. And what am I looking at? Here's my total. I'm looking at 1525 and a half. So I'm looking at 20. Whoa, let's try that again. 25 and a half. And then what do I want to do? I want to cut that bad boy in a half. So what is that? 12.75, I think. So as you can see, when I did right-hand endpoint of this, I was above it. I was right there above it. And you can do it with this one too. Our last one was 7. These are nice to put in because 3 squared 9, that's 10. 2 squared is 4 plus 1 is 5. The last time we had 8, but now we're up here at 15. So you can see how we are above the estimate right here. So this would be fine. I mean, it wouldn't matter if I did n equals a billion or something, you know. Like if I keep going on zeros here, that's a lot. I'm not going to draw that, but it wouldn't matter if you're left or right because these are so thin, I'm going to get a good approximation. But if I'm just doing a couple of these subintervals, one was too low, one was too high, but check this bad boy out. What if we did midpoints? So same idea, same interval, two rectangles from 1 to 3 here. And the only difference is now I'm going to cross at the midpoint. So this is going to come up, instead of the right hand, left hand, it's going to hit right in the middle. It's going to hit right in the middle here. So I'm going to come up, come over, check this out. So it's a little bit above, a little bit below. Hopefully that balances out, and this should be a really nice approximation. Let's do it from, we got from 1 to 3, but with 4. So I'm still going to mark where my rectangles are, but now I want the midpoint of them. So it's like you're hitting the midpoint, so it'll be something there, something there, something there. So see if you can draw these in here with me. So check that out. Oh yeah, got that right there. Coming up, midpoint, and all the way up here. So you can see that's looking pretty good. Like they should cancel each other out. Let's go ahead and finish this off. This is going to be a tough one for me. So 1 to 3. So now I'm divide this into, wasn't these, each one of these intervals a third? And now in those thirds, I'm going to have the midpoints, and I'm going to do the best I can here. Let's start drawing these things. So it hits at the midpoint, midpoint, This is getting rough. Midpoint. Midpoint, and one more. Where's that midpoint? It looks like right here. All right. Whew. So we can kind of draw those in there and get that. So let's go ahead and do this one. So now when I'm talking midpoints, I know it's still this whole b minus a. It's still, I can tell these are still 1/2 wide. So I've still got this 1/2. Now the difference here, what are we putting into my function? Well, I'm not putting in 1 or 1.5. I'm actually putting the midpoint in there. So I'm actually putting in 1 1/4. 1.25 is my first one. It's in between 1 and 1.5. But from there, it's a 1/2 wide, isn't it? So the next one would be a 1/2 from that. So it'll be 1.75. From there, it'll be what's next? 1/2 from that. So I kind of quit looking at the picture and just start adding halves or whatever the width of your interval is. And then this will be the f of 2.75. Woo, that's pretty crazy, huh? So you kind of have to find your starting one, and then whatever it is, you're just adding the interval width to it. Let me show you a cool calculator trick. We could go ahead and still type these in and add them up. But here's a cool trick. If you've got it already in your y1 up here, we've got our equation. I can actually, let's clear all that out. I can actually put it all in the calculator. You ready? So what am I going to do? I can say, if I come over here, I can go y variables. You can actually do y1. So it's under variables. Let me do that again. Slide over to y variables, and it's under functions, and it's the first one. I wish it was easier to get to, but it's y1. And then put in parentheses what do you want to put in there. We want to put in 1.25. So this will actually tell me what that is. It's 2.5625. So I can do that right there. But let's go ahead and do it all. I'm going to go plus variables, y variables, the y1 of what? 1.75 plus, and I'm going to do it again, the y1 of what? 2.25. Just put in parentheses 2.25 plus, let's go one more of these right here, and the last one was 2.75, I believe, and that's going to give me the total. But don't forget the 1/2 in front. I need to times that by that 1/2, and check it out. I've got 10.625. Is that what that was? 625? 625. And that is starting to get to be a pretty good approximation of this. So if you added up all these for the area of this, it's 10.625 as compared to 12.75, which was too high, 8.75, which was too low. I like to call the midpoint one the Goldilocks one. It's just right. It's just right. Not too high, not too low. That's a stretch. And that's it. So there we got approximations. Let's sketch one. I'm going to do one with you and then have you pause and try the other two. Can we sketch just, we're not going to calculate the area. I just want you to practice drawing them. So let's do our whole b minus a thing. So it's going to be 3 minus 1 over 5 intervals. So this, I want left endpoint 5 rectangles over this interval. It's going to be 2/5. So I know I'm going from 1 to 3. I'm doing left hand, so if you want to draw that first one in, I know that's my first one. They need to be every 2/5, or 0.4 if you prefer the decimal. 0.4, so there's a 1/2, so there's going to be my next one. Then where am I going to be? I'm going to be at 1.8. Then I'm going to be at 2.2. Then I'm going to be at 2.6. So once you get the first one is at 1, ooh, that's terrible. Let's try that again. The first one's at 1. You can just add to it. 1.4 will be the next one. I'm talking left hand now, 1.8, and the f of 2.2. So if I was going to break this all out, this would be my what I would write out for all my heights of these rectangles. And then what is this? Is 0.4 or 2/5 out front. That would give me the area. Let's draw these bad boys in. So where does that hit? It hits here. I hope your lines are straighter than mine. And we've got this, and then let's just draw those rectangles in like so, and we're good to go. And the reason I want you to write this out right here, it's actually called a Riemann sum. So we're going to talk about this the next section. This is the Riemann sum, you know, as we write these out, named after a German mathematician, and we're going to talk about it all next time. Don't freak out if you see the Riemann sum. It means make these rectangles your left endpoint, right endpoint, or midpoint. And this is going to expand it, and this is going to kind of be our definition to antiderivatives. All right, go ahead and pause it. Try the next two, see how you do. So I drew my rectangles in, and so make sure you hit the right endpoint on these. I found the intervals is 0.375 or 3/8. And check it out. Look what I did in the calculator. I kind of put that over here. Once I knew it started at 1. I wanted the right endpoint, so I added that 3.75, and then I just kept adding it. And when I drew it, I made my best approximation, tried to make these all exactly the same width the best I could. But you're going to need to be able to find these right here. So just plug in the calculator. Once you do plus 3 or 0.375, you can just hit enter, and it keeps generating the next one for you. Did the same thing over here. Hopefully you find out it was a 1/3. There, each one of these is a third wide, and then I had to do the middle. So if I want to do that, you can just average what's between 2 and 2 1/3 to find that middle point right there. Excellent job drawing those in. Let's wrap this up here. Last one, word problems. And this is going to be on the master check. This is what we need to be able to do. Is what about a table of values? So again, I'm looking at the rate of change. We got water being pumped into a tank. Classic calculus right there. I love it. It's a continuous increasing function. Here are some points for 13 minutes. So this is how fast I'm plugging it in is the R of t. This is some selected time. So I don't want you to draw the picture. That's why I didn't give you any graph paper, but I'm going to show you just for the first time so you can see these points. So if 0 is 7 is here, we've got 4 is 13. We're going to do this totally without the picture, but just for the first one, let's check it out. 6 makes 18, 10 makes 23, and we've got the last one. What is that? 13 makes 27. So something like up here. So here are my dots right here. So this is what they gave me, and they said it was an increasing continuous function. So I kind of want the area under the curve. I don't know what's doing in between here. I know it's always increasing, so it's always going up. It can't go back down. But we're going to use a Riemann sum. So we're going to see this term now, Riemann sum. That's what it's always going to be called. Instead of right endpoint, it's going to be a right Riemann sum with 4 subintervals. So there's my n, and it usually matches up nicely with this. So even without the picture, this is my first rectangle. I'm looking between here and here. So what am I doing? Well, how wide is this rectangle? In this case, it's 4 wide from 0 to 4. And I want a right hand endpoint. Well, what's the right hand? This would be left hand. This is the right side. So it's going to be 13. Well, check it out. So that's great right there. Now do your next one. And what is going on here? Well, now I'm looking at the next rectangle would be this one between 4 and 6. So what is the width of it? It's 2. The x value is 2. And then I'm looking at right hand endpoint, so I'm looking at 18. And maybe I don't think you need to circle that or square that every time. I think you can just keep the pattern going here. So what's the next one between 6 and 10 is again 4 wide. And then what's the right hand? It's 23. And then between 10 and 13 is 3 wide. And what is the height? 27. So there it is right there. If you drew it out, it would be right hand endpoints like this. So that's what we just drew. So you can see the intervals aren't the same, are they? Definitely different intervals on these. But there's still a decent approximation. So we're not going to do the same width in all of them. We're going to use the data. That's going to be our approximation. You can see that this is 4 wide, 2 wide, 4 wide, 3 wide, just like we have there in different right hands. So if it's left hand, we do left side, midpoint we do in the middle. So we could add all of these up. What does it represent if I add these all up? Well, because this is a rate of change, gallons per minute, what would this be? This would be the total gallons of water pumped in the tank over the first 13 minutes. So it's the total. This is accumulation. It's all of that rate of change, just like it was all that velocity. 3 hours at 60 miles per hour, 108 miles. We've got 13 minutes. And that's the total gallons of water. What is that number? I feel like we need to find that number. So we can say 4 times the 13 plus 2 times the 18 plus 4 times the 23 plus 3 times the 27. And what do we get? 261. So that would be 261 gallons. The total number of gallons pumped in over the first 13 minutes. Approximately. Remember, this is approximate. That's not exact. Is this approximation greater or less than? We can only really answer this because it said it's increasing the whole time and obviously continuous. So it has to be going up. So even if it's concave up to concave down or something, no matter how I draw between these, what is the right-hand endpoint in this case going to be? It's going to be too big. So this is actually greater than the true value because it's above it. So I kind of highballed the estimate right there. So we can use table points. So that's something we got to practice. Good luck. I apologize for the tedious work on this one. Use your calculator, kind of speed things up. All calculator, whole packet, mastery check. Good luck on this. Peace out.